So now let us try to calculate this omega. Like I mentioned, calculation of omega cannot be done for any arbitrary system. It becomes very complicated. But I want to show it to you for a particle inside a box. You all must have at least seen this particle inside a box problem from quantum mechanics. Whenever you are studying or started to study quantum mechanics, the first thing that you actually study is what happens to a particle inside a box. Okay. So we will start with quantum mechanics and show you the what is the approximate number, order of magnitude of this particular number, the total number of ways or the energy levels, the total number of complexions possible for a single particle inside a box. We have to start from the quantum mechanical perspective. That will make certain things very clear and make illustrate the fact that this is actually a very, very large number even for a single particle inside a box. And obviously for more particles it's going to be even more larger. So the idea is to illustrate that particular concept. Okay. So we have to do a little bit of quantum mechanics, but not too much. I think most of you will be familiar with the preliminary quantum mechanics stuff that I am going to do here. Okay. So let's take a box and there is a single particle, 3-dimensional box. Okay. And its dimensions are all L. Okay. Now when we talk about quantum mechanics, you have to solve the what equation? Schrodinger's wave equation. The Schrodinger's wave equation has to be solved for this particle, and what the Schrodinger's wave equation will give you, this is the Schrodinger's wave equation written in a very simple form, right? What the Schrodinger's wave equation will give you is this xi, and what is xi? Wave function, and the wave function happens to depend in this case only on the position of the particle. So I am going to write this as R1. Okay, we don't need a whole lot of quantum mechanics. Certain things that I want to illustrate will come out automatically once you see where I am getting at. Okay. Now this is also an eigenvalue problem, right? This is also an eigenvalue problem, right? So this H is actually called as the Hamiltonian, and the Hamiltonian is so the Hamiltonian is minus h square by 8 pi m times dou square by dou x square plus dou square by dou y square plus dou square by dou z square, and therefore the wave equation can be written as follows. Right? H is basically the Planck's constant and m is the mass of the particle. So this is the Schrodinger's wave equation, and if you solve this, you basically trying to find out what possible states the particular particle can exist in. But the states are not as important to us as the values of the energy that it will take. Okay, we want to find out, so we are considering this to be our NVE. There is a volume, there is number of particles is 1, okay, and it has some energy. Okay, the energy that it has is, say, some E star. I don't know what energy, some E star. The idea is, like I mentioned, this exercise is done to show you what this omega number is, how it looks like for a simple case. There will be a pi square.
Because it is minus h cross square by 2m. It is minus
H by
h cross square by 2m. So h cross is equal to h by 2 pi. So you square it, you get h square by 4 pi square.
Okay, fine. So there is a pi square. So there is some detail missing there. So it's probably equal to pi square. Is that right? I don't know. I don't remember the exact form, but that is not really important to us for this derivation. So when you solve this, what do you get? You can solve this using what? How will you solve this problem? Using separation of variables. You can solve this problem using separation of variables, and you happen to get xi to be equal to c into sine nx pi x by L sine ny pi y by L sine nz pi z by L is your xi, and the corresponding e's are the eigenvalues, right? And that turns out to be this. Okay, so h square by 8 ml square right. So this implies right. So if we are given a certain E star, if we are given a certain energy, okay, say for example the energy is maybe 3 times 8 ml square by h square, if this is a given energy, then what values can nx, ny and nz can take? What values can they take? Nx, ny, nz are all positive numbers. So nx, ny, nz are all 1, 2, 3 and so on. They are just integer values. So this is the solution for the Schrödinger's wave equation, and these are the various ways it can have energy E, nx, ny, nz. So the energy depends on these integers nx, ny and nz. Suppose I am saying that the imposed energy on the system is actually 3 times 8 ml square by h square is the energy. Energy is 3, E, nx and y is 3. So you can, how will you get this energy? These will have to be what? Well, if it's, yeah, so if it's, well, okay, I think I need to be a little bit careful. So I think I should pose the question a little bit carefully here. So if energy is equal to 3 h square by 8 ml square, then what values can nx, ny and z take? What can they take? 1, 1, 1, right? Can it take anything else? Can it take anything else? So there is only one way of getting this energy, right? There is only one way of getting this particular energy, right? And the corresponding xi or the wave function will be c sine 1 pi x by L, c sine pi y by L and so on. And of course, while xi by itself does not have any specific physical meaning, xi square apparently can give you the probability per unit volume of finding a particle in some region in the space. Therefore, it is possible for you to find this constant c by requiring that integral of xi square dx dy dz equal to 1. So I think these things might be familiar to you, right? So by requiring that xi square satisfy this condition, it's possible for you to find C, and it turns out to be something in this problem. Okay, but now let's come to the energy thing. Now let the energy that I am imposing is not say it is 6. For example, the energy is 6 h square by 8 ml square. Then what values can n x, n y and n z take? Two, 1, 1, right? Then 1, 2, 2, sorry, 1, 2, 1, and then 1, 1, 2, right? So basically there are 3 different ways the system can have energy 6 h square divided by 8 ml square, and if I increase this number 6 to something else, then I will have a larger number of ways the system can actually have this particular energy. Now remember, for each nx, ny, nz, the corresponding psi is going to be different, right? In the first case, in 2, 1, 1, you had sine 2 pi x by L, sine pi y by L and sine pi z by L. In the second case, there is going to be a 1 here, 2 here and 1 here, and in the third case it's going to be the other one. So there are 3 different values of xi which have basically the same energy, right? So there are 3 different quantum states the particle can have with the same energy, right? And I can keep going on and demonstrating that the number of ways in which you can achieve these energy levels is going to increase as you increase the energy level of the system. Now another thing that you have to notice is that between 1, 1, 1 and 2, 1, 1, there aren't any other energy level. There is no other energy level between these 2 levels, right? There is nothing in between this 3 h square by 8 ml square and 6 h square by 8 ml square, simply because these energies have to be dependent on these nx, ny, nz, which are basically integer numbers, correct? Which essentially is what quantum mechanics is, basically telling you that the energy levels of a system are actually discrete. They jump from one value to the other without anything in between, right? Like what is happening here. Now suppose we have, so this is demonstrating, how different states can exist with the same energy level. Is there any question there? Anything? N is not 0. N is 1, 2, 3, 4. As the solution of this differential equation requires n, if it's trivial, then E is 0, right? So n cannot be 0. Okay. Anything else? Okay.
If nx is 0, xi also comes out to be 0 in that kind of.
That's what. So you can't have 0. The nx, ny, nz, the integers that you get cannot be 0. Now the question is, if some arbitrary energy E is imposed on the system, how will I find out the total number of ways it can get? How will I find out this? Now you saw that this was 3, right? How will I find out for any arbitrary energy E is the question. So that is somewhat a hard problem to solve. So what we can do is, we can actually look at this equation a little bit more carefully. So let E star be the energy, and that's actually equal to h square divided by 8 ml square divided by nx square plus ny square plus nz square, which essentially means E star times 8 ml square divided by h square is equal to nx square, ny square plus nz square. right? In order to try to find out the total number of ways the system can actually have the energy E star, what we do is we look at this equation and realize that it is an equation of a, suppose this is nx axis, this is ny axis, and this is nz axis. This actually is an equation of a sphere. Since nx, ny and nz are all positive, then it is basically the equation of a, we are only considering the 1/8 of a sphere in the positive xyz quadrant, okay, and the actual set of all possible ways. So if this is the sphere, okay, this is 1/8 of a sphere, and there are many of these points here. And so on, okay, they are just filled with these points. If you want to find out how many points are there with this as the energy, then you will have to find out how many points are lying on the surface of the sphere with square root of this as the radius, correct? Is that clear?
Is it just the surface? Yes, because
Yeah, because it's exactly that energy. I want the total number of points at that energy, right? If I take the square root of this, I mean, if I know the total number of things on the surface of this thing, right? Now it is again not possible for us to find out that number either. Okay, what we can do is we can actually look at it in the following manner. So let us write this down again. So So let us now see, we can do this. So let phi let phi less than E star be the total number of points which are less than E star. Okay, total number of points which are all having energies less than E star, right? So how would you calculate that? You can basically do the following, right? You can calculate the volume of this entire sphere, volume of the sphere at this energy corresponding to E star 8 ml square by h square, and divided by the volume of each individual blocks that is actually making up the sphere, right? Making up the sphere, and that would basically tell you how many points are there with energy less than E star ml square by h square. Are you following that? So this is very simple. It's nothing but 4 by 3 pi r cube, where r is my E star 8 ml square divided by h square power 3, that's the volume. And if I have extremely large number of points, then the error that I would be committing in actually dividing this by 1, where 1 is basically the volume of 1. So this would be 1, right? Because all these numbers are increasing only by 1. So either in the nx direction it's 1, in the ny direction it's 1, in the nc direction is 1. So the minimum volume element that is comprising this sphere is actually 1 by 1 by 1. So if I divide the total volume by 1, I would essentially be getting the total number of points which have energy less than E star. Yes or no? No, not following. Not following.
So if we take one sphere with radius of that energy, then it will also include the negative points.
No, you are not taking the, you are not, okay. So the question is, if I take the entire sphere, I am also including the negative points, right? Correct. So I need to multiply it by 1 by 8. Is that okay? Now it's okay. Is that the issue? Okay. I have to multiply it by 1 by 8 here because I am only interested in 1/8 or 1 octet of the sphere. Yes.
So in this case, if the value of the radius is very small,
Ah,
this won't work.
this won't work. If the value of the radius of the energies are extremely small, this approximation does not work. It only works if the energies are somewhat very high. But we will plot and quickly show you that for very quickly, as the energy just increases a little bit from 0.01 kBt, you can actually quickly see the total number of nx, ny, and z will become very large. Yeah, it will just become huge. Okay. So now what we have to do is,
That equation is about 3 by 2.
huh? What is that?
So the radius is square root of the LHS. So
Correct. I agree. Yes. 3 by 2. This is square root, right? This is nothing but this square. Okay. So what was the expression? I need to rewrite the expression now. So now okay. Now we have to find out, this is not the number that we want. We want the total number of points that is going to exist at E star. Right, that is what we are looking for. How many points are there at E star is what we are looking for. Right. So that is again very difficult to get. However, we can do some small approximation. Right. What we can do is, we can calculate phi of E star plus 0.5 some small energy, subtract it from right. Can we do this? This will give us the total number of points that is going to be present in that shell around E star. Right. We are of course making an approximation that the shell thickness is going to be of the size delta E. Right. So we will see what that gives us. You can do anything you want, okay, as long as it's delta E or something like that. Okay. So I'm going to call this entire thing as some L. So I have L times E.
is already used for the length of the box.
Okay, so okay, good point. So maybe L. Now you just take this E star over 3 by 2 outside, 1 plus 0. You can expand this. Terms will be of the order of delta E by E, the whole square minus 1 plus is what you get. So what we call this, let us call this thing as okay. And L is your so this is the total number of points that is going to lie in a shell of thickness delta E around the energy level delta E, the E star. Okay. Now what we have done is actually not very wrong, because when you are talking about a closed system, we are talking about a closed system, but or isolated system. No system is actually isolated, right? Even the act of, if you are trying to measure something from the system, you are actually going to interact with it, and it has to exchange some amount of energy from, for example, if you are measuring the thermometer, you need to allow the system to exchange heat with the thermometer so that you can measure its temperature. So that energy E is always going to be fluctuating a little bit about E or E star. Okay. So in a sense, what we have done is not very far from reality, and you will get some number of states about the energy E star of width delta E. Okay. Now what you can do is, let us calculate the quantity. Okay, yes. What is wrong? Did I miss something here? There is a E star, there is E star times, I think I missed a E star power 3 by 2, right? Yeah, that's why that's a good point, that's important, right? There's a E star power 3 by 2 here. So this becomes 3 by 2 pi over 6 8 ml square by h square delta E star power 1 by 2. Is that right?
So we are not considering the volume of the cell.
Oh, you are, no. This is there right here. Here, in terms of L, you can write the volume, right? So this can be again written as, if you want to write it in terms of again, did I miss something on this? 3 by 2, and this will be volume power power 1 by 3, so 2 by 3 divided by h square so now let us see, any doubts, something confusing, or is okay? Now before we proceed any further, let us try to see how many states, what is this total number phi for a given energy E star, like what is phi less than E star, this particular quantity right here that we just calculated. Okay, so I took m to be 10 to the power minus 23 kilograms. Okay, h is the Planck's constant, volume is about 1 meter cube. Okay, and for a temperature range between 0.01 and 500 Kelvin, taking E to be say kBT, ranging between 0.01 and 500 Kelvin is the temperature, taking T to be in that range. If I take E star to be kBT and substitute it in this expression and calculate phi less than E star for every single case, and I plot it, I get this curve on the right hand side. Is the last bench, can you see this slide? Yes. So this on the x-axis is basically the energy, and I have plotted phi less than E star, total number of points which will give you energy less than E star. So considering which basically consists of all the points inside the entire volume of the octet. So it's plotted in a log base 10 scale. You see the total number of points that you are having here. So for very quickly the total number of points increases and reaches something close to 10 to the power 34, total number of points 10 to the power 34, and we are still looking at only one particle inside the box. Now, is this a large number of states? Is this clear? If I take a particular energy E star and plot the total number of waves, basically total number of waves that are existing up to E star, and plot it for various energies, I get this for various energies for some typical mass and temperature range. The states is 10 to the power 34 and 35. So to give you an idea as to whether the number is large or not, the total number of stars in this universe is how much? Do you know? Some estimate? 10 to the power 21 stars in this universe. For a single particle inside a box, the total number of complexions that you get, not complexions, the total number of states which have energy less than E itself is 10 to the power 35. It's a huge number. Okay, so that octet of a sphere contains an extremely large number of particles. Okay. Now what I did, okay, I plotted, okay, now I just need to do a little bit more to talk about the next slide. So you agree that this is a large number, right? It's a very large number for just one single particle inside a box, and this is obviously going to increase if you have more particles. Now let us calculate the function. Okay, so I need to rewrite certain things. So if you have noted down, can you please tell me what is phi less than E star so that I don't have to keep
5 by 6 8 ml square by
8
m l square
okay,
by x square whole to the power 3 by
times
2 times E star to the power
E star to the power
3 by 2.
3 by 2. Okay, let us calculate the quantity. That would give you right. Now what was our delta phi less than E star? Can you tell me what was our delta phi less than E star? 3 pi by 2, 3 pi by 12. Okay.
8 ml by 3 by 2
E to the power half times
delta E star.
that I. So E star, all that is interchangeable. So now, so if you look at these two expressions, what can you say? They both are just, you can write one, you can write it like this, you can write you will get this. think I should be careful in writing this. Right. So this delta E star about delta E, about with the thickness delta E, is actually our omega, the total number of complexions that it can actually have when it has a certain energy E star, except that now it is about some delta E at constant volume and with number of species being equal to 1, correct? This is actually our omega, except that it is a little approximate. We can't obtain exact values. This is our omega, the number of ways the system can actually take that energy E star, right? We will plot this function. So this function you can plot d phi by d star times delta E by assuming some small value of delta E as well. This one also is a huge number, is in the order of 10 to the power 32, 10 to the power 32, okay, and I think I have assumed some small delta E here, either maybe 0.01 kBt or something like that has been assumed to plot this, showing you that even delta E, even omega is actually in the same order of magnitude as omega less than phi star. There are as many points, almost as many points on the surface as there are points within the volume of the sphere, which essentially means as the radius increases, the energies becomes more closely spaced, right? The energies are getting more and more closely spaced. That is what this tells you. Okay. So large numbers. So we have just seen how large omega is for a single particle in a box. Now we can do the exact same thing when you have more particles in a box. Okay. So that will basically take us to an ideal gas. Now instead of looking at one octet of a sphere, we look at the same one octet of a sphere, however in larger dimensional space. We now need to do the entire calculation with by knowing the expression for the volume of a sphere in 3n dimensional space. So if n is the number of particles, you can calculate what the volume would be of all the particles. That would turn out to be something like this. Okay, this would be the volume of an octant of a 3n dimensional sphere of radius r. Using this idea, you can actually derive omega for a system which has a large number of particles. We will do this in the next class, and then with this we can find what S is, because S is nothing but kb ln omega. With that we can show what happens when we take the derivatives with respect to energy and with respect to volume. We will get back the expressions for pressure that you all would have studied in kinetic theory of gases in your maybe 12th grade, right? You will get exactly the same number for the energy, same expressions for the energy and pressure and all that. Okay. So it's kind of interesting to see that. Again, basically trying to illustrate the point that once you know omega, you can get everything else from it. With that, we'll stop.